Yeah, so today we are for the course Physics 2426 81802. My name is Olena Erhardt. I hold PhD from Moscow University, particularly People's Friendship University. And we start today from a chapter about mechanical waves. So a few words about structure of the course. It might look a little bit surprising maybe, or maybe you might think why we start from volume 1. You know that we use a book OpenStack, green one. I don't have it with me, but you know what book. So we start from volume 1, chapter 16 and chapter 17, you saw in syllabus. Then we jump to volume 2 and start electrostatics. The structure, such structure is because waves, they applied not only in mechanics, but also in electromagnetic theory as well. In that wave theory, wave equations would be exactly the same how we will write them for mechanical waves. Well, for example, for mechanical waves, we'll derive in a few moments wave function y of x t, which is amplitude of the wave, cosine kx minus omega t. We'll discuss all those notations and everything a little bit later, just for right now in general.
What's that symbol?
So, wave equation. No, and basically it is called, a wave function. A wave function. And that suffice so-called wave equation, which is second derivative of that particular function over x twice equals 1 over v squared d twice of xt dt squared. So those round derivatives, they're partial derivatives. If someone did not see them before, no, we'll discuss all that as was said in details. But what I to point out right now, like look, that y of xt, let's take transverse waves. They are transverse and longitudinal. We have transverse are simpler a little bit to describe for certain mathematical reasons, I would say. Yeah, we have transverse wave. Okay, so that transverse wave has for each particle of the string, for example, deviation. So here we have y, here we have x. Could depend on t as well. No. So the part y of x, it shows how it changes with each x, how much deviated from position of equilibrium. Position of equilibrium here, horizontal line. So y of x. So that shows, and that thing stands, that described with that formula, and that satisfies that particular equation, which is called a wave equation. For mechanical waves. Okay? Now, we'll study later on electromagnetic theory based on Maxwell equations. And at the beginning, maybe some things would look complicated for you. but we will come at the end. All of you will be able to write down those Maxwell equations, and on top of that, you will know what is the meaning of those equations. Now, let me write down those equations again. Don't get scared or anything. You just see how they look like. So there are 4 equations, Maxwell equations. So first, for electric field, dA area. So that would be Q net or Q enclosed. Different notations, enclosed over epsilon 0 certain constant. So second equation for D, dA 0. So we have 2 fields, okay, E and B in electromagnetism. Electric field, magnetic field. Probably you heard about those notations and those fields for sure. No, and 2 more. So another one for E circulation of vector E. So that is just minus d B over, I'm sorry, it right now through B A, but if B over dt law of electromagnetic induction and generalized Ampere law, BDL mu 0 I and plus mu 0 epsilon 0 dFE over dt. That was something like that. So that is current of conduction. That is so-called current of displacement. Let me double check. Constants. 0 epsilon 0. Yeah. No, and sometimes we write here enclosed. No, enclosed current. So it is just, we'll study later on. That's what I'm telling you, what you will achieve in this course. Now, you don't know what those equations means, what they're about. We just know that they're Maxwell equations. At the end of the course, all of you will be able to write down those equations, those Maxwell equations. They're in integral form, could be in differential, but those more complicated you will study whoever is interested later on. All of you will be able to write that system of equation and understand exactly what's going on with those electric and magnetic fields. Okay. More of that, I would say, you will see the world differently. You will see more details, and in general, I would say that in this course, I invite you to expand your view of reality in some sense. Yeah, so those vectors E and B, again, going back to the structure of the course, for them, the same like for the deviation from position of equilibrium, you can write also wave equation. Exactly the same mathematically. So when electromagnetic wave propagates, you see it like those vectors E and B, they would satisfy that wave equation. Not, for example, let's take component EX, we write for components of the field. We will write accordingly second derivative of the component let me write a little bit better, of Ex over dx twice, and they will take x because, you know, we see what's going on in x direction, would be equal 1 over v square d twice Ex over dt square. You see exactly the same structure of the equation. So over there, how much it goes from position of equilibrium on the string, each part of the string. Here, what is the value of that electric field? How big it is? Larger, smaller, stronger, weaker. But structure is the same. Then that constant on those waves small. It's what we see in reality. A few kilometers per second, meters per second, maybe miles per hour. This one huge, and this is special. This is speed with which all waves travel, I mean electromagnetic. And that is speed of light. That was proven by Maxwell whenever he came to that conclusion. So instead of v, because it is so special speed, speed of light, no, 3 by 10 to the 8th meter per second, we can write and more exactly 299 792 458 meters per second. Okay, yeah, that is correct. So that is huge. That's the only difference of this equation and that equation for mechanical waves. So that's why we will study first properties of waves, concentrate on, you know, derivation of that equation and all of that. No, and sound waves also on the way we'll see, because see, for example, that on string it is transverse. That is, remember, always electromagnetic waves, they are transverse waves. They are never longitudinal. So transverse waves, wave propagate in one direction, oscillations in perpendicular directions. So it propagates like that. Transverse. Longitudinal, it propagates like that, in the same direction, vibration. That's why it's kind of, we describe it mathematically a little bit harder than transverse, and so we'll derive all the theory for transverse first. And keeping all that in mind, we'll start with chapter 16. Next lecture, chapter 17, sound waves, which are longitudinal always. We'll discuss those. Also, another interesting thing of waves, some transverse waves, particularly electromagnetic waves, they might go in medium, but they don't require one. They can go in empty space. For example, between stars, you know, in space with in vacuum, they can propagate. So they don't require a medium. A longitudinal, those like sound waves, for example, what I speak, I compress, rarefy, and those vibrations you hear sound, and your eardrums, they sensitive to the change in pressure, for example. In those vibrations you can hear sound. That always require medium. So longitudinal always require medium. Even from there, if you forget what kind of waves, electromagnetic waves, you will remember that they should be transverse, never longitudinal. Always transverse. So for electric and magnetic field. Okay, so